Welcome to another video of math problem solving. This is Bharat Divyang. This video though is not about solving as much as it's about a problem. Let's get started. What's the most beautiful equation in math? I know what you're wondering. How does one even think about beauty and math together? And how does an equation turn beautiful? There's a saying in English, beauty lies in the eye of the beholder. My hope by the end of this video is to turn you into that beholder who can look at this equation and actually say, yeah, maybe it's really beautiful. How does one even define beauty in math, right? So these are the things that kind of hovers in our head. So let's see how we can take this forward. So once upon a time, long, long ago in human history, even before prehistory, even before what we wrote down, what we passed on, we were probably hunter-gatherers. Right? Nobody knows the truth. These are scientific theories that's proposed and tested and evidence gathered around to support the hypothesis that once upon a time we were hunter-gatherers. Do you think there was a need for numbers then? Probably not. Every day life would go on. We would just hunt, gather, eat, live. That's about life. There's no need. There's nothing that accumulates. There's nothing that you need to keep stock of. And therefore, the need for numbers might have been almost unnecessary. Or even if it were there, it would be like extremely elementary. From there, we turned into pastoralists, which is essentially sheep herds and goat herds and cow herds, where probably for the first time, the shepherd would have to keep stock of how many sheep he had. Or when we turned farmers, when we had to keep stock of how many bags of grains we had. And that, I think, was probably the genesis of how numbers were born. And this is again my theory. There are many out there, but this is my theory that we probably started with one. There would have been one, earth-shattering, completely mind-bending invention with numbers, and the rest of them would be an evolutionary change over it, kind of applying it step by step to take on to the next level. Right? So, what do you see here? They're like this bunch of symbols. Okay, and then this bunch of symbols, you might recognize some of them, you might not, with many others, but they all represent one thing. Can you guess what it is? The answer is that it represents the number 1. So every single symbol there represents the quantity 1. This symbol that you're looking at your screen right now is the symbol in the Hindu Arabic numeral system. This is how we represent 1 today. But each and every one of these symbols in different cultures and different languages represents 1. So 1 is a concept. It's not just a number. It's a concept of signifying the quantity of something. Remember, I always tell you, human intelligence is about knowing the differences between similarities and similarities between differences. So the moment we could differentiate things and we said this is labeled as a sheep, then the next step would be to count it as 1 versus many. So whoever came up with this idea, whoever invented 1, whoever discovered 1, must have done an earth-shattering, mind-bending invention for their times. So definitely, this is the birth of the number system. A while later, after we invented different types of number systems, from the Roman number system to the Hindu system to hexadecimal systems, we still didn't have the concept of 0 until it was invented in India, where what happens if you actually subtract entirely? What are you left with? How do you represent it? And that's 0, which is also a monumental invention when it comes to our understanding of math. The next one, and by this time you should already recognize that we use symbols to represent ideas. And one such idea is represented by the symbol, the Greek letter pi, which has a numerical value of 3.141526, so on and so forth. which is nothing but the ratio of the circumference and the diameter of circle. Which circle? Any circle. Whether it's the minutest of circles or circle drawn at the scale of a solar system, the ratio of the circumference and the diameter is a constant, and that constant numerically is 3.1415926. Symbolically is represented by the Greek letter pi. This is what we call as an irrational number because it's non-terminating and non-recurring and can keep going on and on and on. Another number is in the letter E. I'm not talking about the numbers written here 1 and 2 to kind of indicate how to write the E. I'm talking about the number that the letter E represents. This is called the Euler's constant, and its value is 2.7182818828. So on and so forth. This is also irrational and non-terminating, non-recurring number, just like pi. What does E represent? E is a number which is essentially seen when we compound things. So in the study of compound interest, you would realize that there is some level of a natural constant limit called E that you would come across. To know more about it, you should check it out when you get a chance, either on YouTube videos or when you come across this in your higher level math. But for now, for all practical purposes, remember that E is a symbol that represents another constant that we see when we think about compounding things, when we think about growth. What is I? Interesting. So there are a lot of symbols in math. So 3 times 3 is 9. 3 times 3 is 9. 3 square is 9. The square root of 9 is 3. So if I want to go from left hand side to right hand side, I'll say square. 3 square is 9. If I want to come from right hand side to left hand side, I say square root. So square root of 9 is 3. Similarly, minus 4 times minus 4 is 16. The square of minus 4 is 16. The square root of 16 is either plus or minus 4. So the question we posed is, what multiplied by itself would give me minus 1? If the left hand side is negative, I know what to do with it. But if the right hand side is negative, what is the square root of minus 1? And there is no real number which can actually satisfy this condition. Not a single number in the number line that can satisfy this condition of multiplying itself to give you minus 1. And that's when we had to invent a symbol I to represent the fact that I square is minus 1. So each and every symbol that we've come across so far, whether it's 1, 0, pi, E, or I, are each one of them monumental in itself. It's amazing. It's mind-bending. They are magnificent steps in a human evolution or in our understanding of mathematics. So imagine if we can get all of this together. Now, you have to understand that each of this is very different. So there's a very famous meme where I is actually unreal because it's not on the real axis. And pi is not rational. So when I and pi meet each other, they say, hey, I says be rational to pi because pi is irrational, and pi says get real because I is unreal or imaginary. Right? So you have all these number systems. You have all these different symbols. The most beautiful symbol, a beautiful equation in math, is the one that connects everything together. It's represented like this. E to the power I pi plus 1 is 0. It literally gets all the 5 symbols which we have discovered across history and which have such varied properties. You know, E being a constant, pi being a constant, I being an imaginary number, E and pi being irrational, 1 and 0 being so fundamental to our number system. They all somehow come together in this beautiful equation. The reason I want you to, just take a moment to think about it. If you have an irrational number and you do any operation on that, for example, if you take root 2 and you square it, it's still irrational. Root 2 square is 2, so that's rational. But typically, if you would do anything, any kind of operation, root 2 plus root 3, that would be irrational. Right? If you take any operation, it's very rare that you see the nature of that particular number changing. So you're taking an irrational number, you're raising it to the power of a complex number, which is actually the product of I and pi, which is also another irrational number. and you're adding 1 to it and you get 0. This is the most beautiful equation in math, for the sheer reason that it connects dots in so many different levels. And today, if I can leave you with a sense of wonder and a little bit of curiosity, say, how does it even work? How does this even function? How is this even possible in our universe? Then maybe I've done my job to some extent, to an iota of an extent, to help you wonder and take this forward and search for the answer of why is this even true. And hopefully, you will have many, many epiphanies as you go along in life. At different stages, you'll understand a little bit more, a little bit deeper of this particular equation, and the beauty of it will only keep increasing. I hope you enjoyed this video. If you could share your comments in the comment section, that would be lovely. Thank you so much. Until the next video.